In lesson 5-4, or 5.4 I should say, we're going to look at taking derivatives of exponential functions. And basically what we're talking about here is functions that are like y equals e to the x or y equals e to the u, where u is some function of x. So let's get started. Officially, our textbook tells us that rule number 1 is that the derivative of the function e to the x is e to the x, which is very convenient. That's kind of an easy derivative rule to remember. But let's find out more about where this came from. Well, it all starts with that definition of derivative. And remember, we really don't use that definition of derivative because the rules that we've learned are much more efficient. But here's that definition that we learned way back in at the end of chapter 2. That if you want to find the derivative of a function, you have to take the limit of this difference quotient, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. So what we do is we put e to the x into this formula. And I'm going to go through the process just so you can see that this derivative isn't a fluke, that it does follow the definition. So we put e to the x in for our f of x, and the difference quotient looks like this. The limit as h approaches 0 of e to the exponent x plus h minus e to the x over h. And we can factor in e to the x out of this quantity on top. And then, in fact, we can move that e to the x out to the front of this limit because it's just a multiple that doesn't involve the letter h. So the real limit that we need to explore is the limit as h approaches 0 of e to the h minus 1 over h. Unfortunately, if you just do a straight substitution and put in 0 for h, you end up with 1 minus 1 over 0, which is 0 over 0. And remember, we found out that was an indeterminate form. So we use things like factoring and multiplying by a form of 1 to resolve those limits. In this case, we're just going to take a look at the graph. So when you graph that function e to the h minus 1 over h, this is the graph that you get. And notice if we call this the h-axis, and this is the y-axis, as h gets close to 0, the y value gets close to 1, right? So what we're saying is the limit of that function from either direction is 1. So that expression that we had earlier is really just f prime of x equals e to the 1 times 1. Oh goodness, I got a typo here. This should say e to the x. E to the x times 1 is e to the x. I guess I sort of slaughtered that one, didn't I? We already had an e to the x out in front of the limit, right? And then we found out that the limit value was 1. So e to the x times 1 is e to the x. And so that's where this formula for the derivative that I just showed you came from. The bottom line is if f of x equals e to the x, then f prime of x is also e to the x. This is a formula for the rate of change at given values of x. Let's do some derivatives. See if I can do a little better job on that. So the first function I'm going to examine is x squared e to the x. And you'll notice this is a product. So I've written it here just to give me a little more space. It's a product rule. Usually what we do is assign u and v. So if u is x squared, u prime is going to be 2x, right? And if v is e to the x, v prime is also e to the x. That's the cool part about this derivative. Now to find f prime, we use our product rule. We do u times v prime, which is x squared e to the x, plus v e to the x times u prime, which is 2x. I'm going to write the 2x out in front here just to make it look a little nicer. And I'm perfectly comfortable with that answer for this problem. You may also see it in factored form. Notice there's an e to the x common to both terms, and there's an x common to both terms. So you might see it written as e to the x times the quantity x plus 2. Either way, we have found the derivative. Let's try another one. This function is a little more interesting. We've composed e to the t plus 2 inside the function u to the 3/2. So let me give myself a little more space and then we'll attack this problem. So we're going to need the chain rule on this thing, and there's a couple of different ways to attack the chain rule, but one way is using this u substitution that we've been practicing. So I'm going to say u equals e to the t plus 2. And then my function g, or y, whatever you want to call it, is going to be u to the 3/2. And then what we do is we find these two derivatives and multiply them together. So u prime is simply e to the t plus 0, because the derivative of 2 is 0. And we'll do the power rule for g prime. G prime of u is 3/2 u to the 1/2. And then we're going to multiply these two things together to get our g prime of t. And that's just going to be 3/2 u to the 1/2 times e to the t. Now you don't want to leave a u in your answer because it's a function of t. So let's just substitute back in what u equals. So the final derivative formula is g prime of t equals, I have my 3/2, and I'll move this e to the t over with the 3/2. And then I have u to the 1/2, which is just a square root. So I'm going to go ahead and put a radical sign. The square root of u is e to the t plus 2. The square root of e to the t plus 2. So this guy right here is a pretty good form for that final derivative formula. Now the chain rule also applies to the derivative of exponential functions. And sometimes you'll have a function in the exponent. We haven't shown that yet, but we're going to show it now. When that happens, you have to multiply by the derivative of that exponent, just like the other chain rule problems. In general, we say that the derivative of e to the u is e to the u times the derivative of u. Very similar to the chain rule that we had for our polynomials. So let's do some more derivatives. We start with f of x equals e to the 2x. And I'm going to write it up top so I can have a little more room. In this case, we have a composition, and here u equals 2x. That means u prime is 2. And so I can simply write this derivative as e to the u, which is e to the 2x, times 2. But we usually put that 2 out in front as a constant multiple. So the derivative of e to the 2x is 2e to the 2x. Let's try e to the negative 3x. The derivative works a lot like e to the 2x. In this case, my u is the negative 3x, right? The derivative of negative 3x is negative 3, and we can write this derivative out as f prime of x. That's equal to e to the u, which was negative 3x, times the derivative of u, which is negative 3. And again, I'm just going to put that multiple out in front, that coefficient. And you get negative 3e to the negative 3x. Hopefully you're seeing a pattern here for those kinds of problems. Now I noticed as I was typing this thing out and preparing the video that I made a typo right here. This letter is supposed to be a T, and I just wrote that to remind myself. So I made a typo. But the function that we're exploring is f of t equals e to the 2t squared plus t. This one's a little more complicated. Again, I've set up the function at the top so I can work on it. Again, we have an exponent, which is u equals 2t squared plus t. The derivative is slightly more complicated than the ones we did in the other examples. What is this? 4t to the first power plus 1, because the derivative of t is 1. So when we write out this derivative, f prime of t, we're going to have e to the u, which is e to the 2t squared plus t. Then we have to multiply that by u prime, which is the quantity in parentheses, 4t plus 1. And usually I would write it like this. No, I think I'm going to leave it. I think I like it written like that. Put the e to the 2t squared plus t out in front, and then multiply by 4t plus 1. Okay, let's try one more with a product rule and a composition. Notice we have two functions multiplied together here, so we have a product rule, but we also have this composition. You've been very, very patient, and so we'll kick this one out, and I think we'll call it good for this video. So let's divide this up, and as we go we have to be careful, but this is a product, so I'm going to make u equal x and v equal e to the negative 2x, just to get myself organized. I know that u prime is 1, but here we're going to be careful. V prime has that composition. But we practiced this one earlier. The derivative was something like negative 2x. Nope. Come on, man. How about e to the negative 2x times negative 2? That sounds better. So I'm going to make it negative 2e to the negative 2x. I believe the one we did in the example had a negative 3 there, but the strategy is the same. So when we go to write out our f prime of x, we use the product rule. U times v prime would be our x times negative 2e to the negative 2x. And I'm just going to write this in sort of the standard order, which would be negative 2x e to the negative 2x. That's u times v prime plus e to the negative 2x times 1, which would be e to the negative 2x. This is a perfectly reasonable way to write that answer. However, I want to warn you that you may see it in factored form. In this case, we factor out an e to the negative 2x, and then we have a negative 2x plus 1 left over. You may even see that written as 1 minus 2x. Same as negative 2x plus 1, right? So either of these would be reasonable ways to write that derivative. I guess I lied. I do want to talk about finding the equation of a tangent line. Remember that when you find the equation of a tangent line, our real goal is simply to find the slope so that we can write the equation with y minus y1 equals m times x minus x1. That's the point slope form, right? So here's our x1 and here's our y1. Our job will be to find m. And we're going to use this function and take its derivative to do that. So my point is 1 and 1 over e. I just need to remember that function that we're talking about. Must find the derivative so we can get the slope. Let me remind myself that the point was 1 and 1 over e. I think I might forget that if I don't write it down. Okay, so the derivative here, f prime of x, if we follow our rules, it's going to be e to the u, which is e to the negative x squared, times the derivative of u, which was going to be negative 2x. That's our derivative formula. And since we want to find the slope at this point, we're going to plug x equals 1 into our formula. So for us, our m is e to the negative 1 squared times negative 2 times 1. Now be careful here because this negative sign is a constant multiple, negative 1 times x squared. So this answer is really e to the negative 1 times negative 2, which would be negative 2 over e. Okay, that's our m. Alright, so let's get the equation for the line. We have y minus y1, which is 1 over e, equals m, which was negative 2 over e, times x minus 1, which is our x1. So those are the values we plug in, and then we can do a little math to simplify this. I'm going to have y equals, I distribute the negative 2 over e times x. That's going to turn into a plus 2 over e, and I add 1 over e, and that's going to end up being plus 3 over e. And unless I made some crazy mistake with my arithmetic, that's going to be the equation for the tangent line. So hopefully this gave you a good overview of finding the derivatives of exponential functions, specifically e to the x and e to the u. Good luck.